Well, hey there, and come on in. Welcome to the GameDev Tavern. If you like creating games from scratch, you've arrived at the right place. My name is Nicholas, and this is episode Lucky 13 in the tutorial series where we create a 2D arcade soccer game from scratch in Godot. And welcome back, fellow traveler. This is going to be an exciting episode where we are going to start drilling into the world of shaders. So currently, we've been able to spawn our various players, our two teams, but they currently all look alike, which is going to make it a little bit difficult to differentiate between the two teams. So I thought this would be a perfect opportunity to introduce the concept of shaders in this intermediate tutorial and write a shader together that will allow us to create characters that have personalized jerseys and skin colors. So first, let's spend a bit of time discussing together what shaders are and how we can use them to our advantage. All right, so this is going to be a very lightweight introduction to shaders. I find that topic fascinating, and we could actually spend hours and hours drilling deep into shaders. But because shaders are somewhat complicated, this episode might actually go a little bit over the 30-minute mark. I was actually thinking of doing a dedicated 10-hour course just on shaders at some point in the future. So if you are interested, please do let me know in the comments. So anyways, what the heck are shaders, and why have they become so important in game development? Well, let's start with what we are familiar with, our Godot application. So currently, whenever we create scenes and nodes, there's a series of functions that Godot allows us to use, such as input handling, physics processing, or even just regular processing, that get executed over and over again as part of our gameplay loop. So you're familiar with these, right? Like we use these functions to affect properties of all of our game objects to create some sort of gameplay. For example, we move the ball by affecting its X and Y position in our ball script. We move the player and we set its state. All of that logic, which we write in our code to create or update these game objects, is currently being handled by our computer CPU. Note that as part of this pipeline here, there's actually some hidden additional functions that exist, but that are unavailable to us to override and implement, such as the draw function. The game engine just completely takes care of that for us, so we don't need to override. But just keep in mind that there are some functions here that exist that we don't have access to. Now, these functions are executed in a specific order, and oftentimes they're done as fast as the CPU can handle them in order to just match the frame rate. So for every object in our game, we just go through the same gameplay loop over and over again. Now, at the end of one loop, after the process method, our game reaches a state where all of the objects are in a specific position with various properties applied to them. And so the only thing that we now need to do is to have our GPU display them on our screen at the right position. So how does that happen? What does exactly Godot send to the GPU? Our GPU mostly cares about rendering things. It doesn't really care about the ball's velocity or the player's current state. So in fact, we're not going to send it all of the game information. All of the GPU actually cares about are what we call visual primitives. And this includes things like meshes and vertices, textures, and so forth. Now, you've probably heard a lot about meshes and vertices in the 3D world, and we often don't talk about that in the 2D world. Oftentimes, we only talk about individual pixels. And while those are very interesting visual primitives, there's actually a few other primitives even in our 2D world that we don't often talk about. So keep in mind that in Godot, every single visual object on the screen that you see actually has an underlying 2D mesh with associated vertices. For example, here, when we put a sprite 2D in the game, the image is actually provided to the screen by the process of applying a texture on the face of a 2D quad mesh. And so that quad mesh itself is comprised of 2 triangles and 4 vertices, 1 vertex for each corner. So while we often talk about our pixels in our 2D world, we actually have a ton of geometrical information and visual primitives. Our world is just full of meshes and full of vertices that our GPU will use in order to render our objects. So let's go back to the previous screen. And this time, we're only going to keep the stuff that our GPU cares about. So I'm just going to keep those vertices here. So at the end of our frame processing in Godot, we end up with an initial set of visual primitives like meshes and triangles and vertices that can be passed over to the GPU in order to be displayed on the screen. So what happens when we send this information to our GPU? Well, Similar to how we had this processing loop in Godot with multiple steps involved, like input and process and physics process and draw, our GPU also has a series of steps that take place in order to render objects on the screen. And when we take all of these steps together, we call this the graphics rendering pipeline. So our application starts off by sending all the vertices of our objects to the GPU. The GPU then starts going through a series of geometry operations called vertex operations. It basically processes those vertices by executing various operations or functions that can affect the vertices' positions. And that will also create triangles between the vertices and other types of operations. We won't go too far in details into what each of these operations do, but just keep in mind that in this first stage is all about vertices that define the geometrical shape of our objects. So similar to what we saw earlier in Godot, where the draw function wasn't available to us and completely handled by the game engine, a lot of these functions that are executed as part of the vertex operations are also handled automatically by our GPU. So I'm going to gray them out. Except for a few functions, which the GPU actually makes available for us to pick up and write. Similarly to how Godot allows us to override the process function. These functions are called shaders because historically the GPU made them available to allow developers to use them to shade 3D scenes. So out of those functions that are available to us, the most common function that people use today is called the vertex shader. So the vertex shader is simply a function that gets called for every single vertex and provides the developer a chance to catch the vertices on the fly on the GPU and transform their attributes, such as the color, the texture, the position, the direction in the space where they live, and so forth. And so as a result, it just allows all of the original objects to be distorted or reshaped in any manner that we want. So again, back to the player mesh that we had, it is currently comprised of 4 vertices. So the vertex shader will be executed 4 times, once for each of those vertex. And so we can override this function and add some simple code. For example, this code can say, if I, as the current vertex, if my position is above a specific threshold, then I will go a little bit further away from the center. And so this would result in the distortion of our image. And this is a very common technique to simulate things like grass movement, character animation, object morphing, ocean waves, and the list just goes on and on and on. Vertex shaders are just super powerful to be able to modify the geometry of objects on the go. All right, so back to the rendering pipeline. So once we have finished going over all of the vertex operations, our object shape is completed and finalized, and it will never be updated after this. So the next stage is all about taking those geometrical shapes that results from the vertex operations and preparing them for our screen canvas. So we don't have fine-grained control over these operations, and the GPU does most of the work for us. So here, the first operation that the GPU will do will be to clip the geometrical shape so that its contents fits into our viewport. And then it'll do some projection math so that it appears correctly on our flat screen. And then the GPU will rasterize the image. Rasterization means that it will convert this vector-based shape into a grid of elements that we call fragments. And these fragments are data structures that contain all the information necessary to draw a pixel on the screen, such as the depth, the color, the texture coordinate, the alpha channel, and so forth. And so the next stage of the rendering pipeline is called the fragment shader. This is also a function that we have access to and is very commonly used. This function gets called on every single fragment, and it allows developers to modify the fragment information, such as the color, the depth, the texture coordinate, and so forth, which in turn directly impacts the pixel that is associated with it. And finally, the last stage is a series of operations called the per sample processing, which is completely handled by the GPU as well. Its purpose is to just clean up and optimize this output of fragments, discarding those that don't need to make it to the screen, and then just sending out an optimized list of fragments to various frame buffers before the image is displayed on the screen. We're not going to spend too much time discussing this stage. So, look, I know that this rendering pipeline is a lot of information. The only thing I want you to remember today is that the GPU provides one function for us that allows us to modify the vertices of the geometry of an object called the vertex shader. And then it also provides one function that allows modifying the information for each pixel, called the Fragment shader. So in our game, we're interested in changing the colors of the pixels on our character sprite. So we'll actually be using the Fragment shader, and we'll be passing it a few additional properties so that each pixel can be colored properly. All right, so how do we write these functions, these shaders, and how do we pass them to the GPU? And how is that code different from the various GDScript code that we've been writing so far? Well, do you remember how I said that the vertex shader was run on every single vertex and the fragment shader was run on every single fragment? If we were to go back to our character sprite, that would mean that the vertex function is actually called 4 times, once for each corner of our mesh. And the fragment function would be called almost 300 times, once for each rendered pixel of our sprite. Now, the only way that the GPU is able to execute this fast enough to make sure that everything stays smooth is to actually execute the 4 vertex functions in parallel, and then to also execute as many fragment functions in parallel as it possibly can. The more modern the GPU, the more threads it can just spin up to handle all of these shaders in parallel. However, this parallelism also means that writing shaders comes with a few restrictions. First of all, it means that when we execute a fragment or a vertex shader, it doesn't have access to the information from other vertices or other fragments. They could have already executed, they might execute in the future, but those things are also objects that will get modified roughly at the same time, so it's impossible to access their information. So executions of shader code is all done in complete isolation. Second, the vertex and fragment shaders can only modify the existing geometry, what is related to them, not create new or delete existing geometry. So within the execution of a vertex shader, we'll only have access to that specific vertex that it's being executed for and some properties around that vertex. And similarly for a fragment, it will have all of the data related to the specific pixel that it's coordinating for, not any other pixels. And the last consequence is that there's no notion of memory or statefulness from prior executions. Shaders are completely stateless. But this also means that shaders are very predictable, which, from a specific set of inputs, you will always arrive at the same output. So with this type of restrictions, it usually means that we need to think a bit differently when writing shader code than we would when writing your typical Godot code. And oftentimes this means just being a little creative with mathematical operations in order to create something interesting. You can hop over to shadertoy.com to see some really interesting shaders that people have created over time. Okay, so back to our game. Let's talk a little bit about what we're going to be doing. So we currently have a player sprite. Our objective is to not modify the geometry, but only to recolor the pixels. So for that, we are simply going to write a fragment shader. If you look at the sprite closely, you'll see that the shirt is made of 2 distinct grays, the shorts is made of 2 distinct blues, and the socks are made of 2 distinct reds. So in total, the clothes that are being worn use a palette of exactly 6 colors. And I'm going to be calling this color palette the palette of reference. Now, each country is going to have a different set of 6 colors for their jerseys. So I've actually created an image that contains all of the palettes for all of the countries. And each country's palette is placed on a separate row. Now, remember that fragments shaders are executed for every single fragment. So for the sake of understanding here, we'll just look at an example for this specific fragment. Here, a pixel on the shorts of the player. And the objective will be to recolor that pixel so that it matches the German team. All right, so let's talk a little bit about the algorithm. So we're going to be passing 2 inputs to our shader. We'll be passing our palette texture, and we'll be passing the name or the index of the country that we're targeting. So in this case, Germany, which we currently know is on the 6th row. So we could be simply passing the value 6 here to our shader. So within the fragment function, each pixel in isolation is going to do the following steps. First of all, it's going to look at that palette texture, and it's going to go look at the first row. It's going to loop over each pixel to find which column this piece of clothing refers to. So we do this simply by comparing the color of the pixel, which is this darker blue, with the colors of the pixels on that first row. So here, this is a light red, light blue, and boom, we found that color. It matches what we have. So we know that we found the column that we need to look for. And then because we have the country, we can just find the pixel containing the color that we should replace the current fragment with. So here in this case, we know that Germany is on the 6th row, so we can just do a lookup of that pixel color. And we now have this black that we can use to replace the current color that we have. Okay, so with that done, I think we're ready to write our shader, and I'm going to go pretty slowly because shader code uses a language called OpenGL shading language, which you may not be familiar with, but I'll be sure to explain everything along the way so that everything makes perfect sense. All right, so back in Godot, let's start by creating a new folder in our resources here, which we will call shaders. Might have more than one down the line, and then right click on shaders, create new resource. And then here I'll have you type shader. So first you'll notice that there are two options here, shader and visual shader. So in Godot, you can create your shader either through code or through a graphical interface where rather than writing code, the various inputs and math functions and so forth are just represented by nodes that can be joined together to create some form of graph. At the end of the day, that graph gets translated into shader code. Both of those options are completely equivalent. I will say the visual interface does provide some nice visuals, so anyone who's not comfortable with code might actually prefer that option, and you might actually see a lot of tutorials online that use the visual shader. On mine, I do think that as soon as there's a lot of visual nodes, it can quickly be hard to fully grasp what's going on. So on our end, for the sake of education, we're just going to go and write the code directly. So let's go ahead and pick shader instead. And then here it will ask us for a couple of options. Let's keep those by default. We're just going to give it a name, and let's replace the name with replace_color. All right, and if you double click on that shader, you will see that the shader here loads up in this editor. So first of all, you'll notice that it's a different editor than our regular code editor. First of all, it's located at the bottom of our game screen here. We can see both the gameplay and the code. The reason for this is that this allows us to see in real time the effect of the code that we write here on our shader on the visual elements that it's affecting. It's a nice way to have some quick feedback loop. You'll also notice a couple of other differences here. There's no possibility of adding a breakpoint on the side, simply because we can't pause the execution of a shader on the GPU. There's also no Godot documentation when you try to control-click on some of those keywords. And again, the reason for this is Godot's shading language actually is a subset of the OpenGL shading language, so all of the documentation can be found there directly online. It's always being kept up to date. However, there's a couple of things that hopefully should look familiar to you. So first of all, there's function vertex here, and there's a nice comment here that says that it should be executed for every vertex that the material is visible on. There's also a fragment function here, which again is going to be executed for every pixel. Now, I mentioned before that the vertex shader and the fragment shader are going to be executed at very different times of our rendering pipeline. So these things don't really have anything in common. So isn't it interesting that both of those functions are located within the same file here? Why would they ever be side by side? Well, the reason for this is that when writing shader code, there's actually quite a lot of boilerplate, lower level initialization code that needs to be done when writing a vertex shader or a fragment shader or any type of shader. And so rather than have us do all of that work, Godot is nice enough to actually take care of all of this. It's just providing us with just the functions that serve as entry points. These are called processor functions. And then Godot will just take whatever code we have written here and just plug it into the vertex shader and the fragment shader that it's actually going to pass into the GPU. So if you look at the first line here, shader type, Depending on the type of shader that we're writing, the initialization that Godot needs to do at the GPU level, so all of that setup and all of that boilerplate, is actually going to be quite different. There's 5 different setups that Godot can perform and provide out of the box. You can read about that in the documentation, but basically, Godot can provide a setup at the GPU level for a generic 3D shader. This is the shader type spatial. A different setup for a generic 2D shader, a different setup for rendering particles, a different setup for rendering skies, and a different setup for rendering fog volumes. So depending on what you want to work on, you'll specify a different shader type, and then Godot will take care of all of the initialization that needs to happen at the GPU level so that your shader works properly. On our end, we want to work on 2D elements, so we actually need to have Godot configure the shaders for us that way, and so we need to specify the shader type not as spatial, which would be for 3D element, but as canvas item. Okay, so we're actually not going to be modifying the geometry here of our mesh, so we can get rid of this code, and we can also get rid of this code at the bottom here. So let's go ahead and save. And we want to be able to see the results of, the code changes here live on our player sprite. So let's hop over and open our player scene and then pick the player sprite here, and then hopping over into the material property, click on material, click on new shader material, and scroll down here. And then in the shader property, you can drag and drop the replace color shader that we have. Okay, so the shader now is being applied here, and because we're not doing anything in the fragment function, the pixels are not being modified. But within this function, and remember that this is going to be called for every single pixel out there, there's a lot of properties that we have access to about the current pixel that the function is being executed for. And the one that we care about the most here is the pixel color. And we access that through the property called color in all capital. And color is a property that can be read or written. And in shader code, this is a vector 4. It has 4 properties, red, green, blue, and alpha, and each of those range from going from 0 to 1. So for example, if we wanted to change the color of every single pixel, remember this is executed for every pixel, so I'm going to say I want to change the color of the current pixel to white. I would just specify that this is a vector 4 with all of my values set to 1. Okay, don't forget the semicolon at the end. And then you can see, I didn't even save, but you can see the result here on our sprite. All of the pixels of the image are now replaced with white. But let's say that we wanted to tweak this code a little bit so that it would only affect the transparent pixels of the texture. We could just do a simple lookup of the colors alpha property and write something like this. If my colors alpha property is equal to 0, then execute this code. And now you can see that only the transparent pixels of the texture are being affected and turned over to white. All right, so let's go ahead and clean this up for now, and we're going to write our fragment shader according to what we spoke about earlier. So we need to pass in 2 properties to the shader, and we can do this by specifying them at the top. So the 2 things that we'll need are the image that contains all the palettes for the various countries, and then whichever country we want to do the actual swap with. So in GDScript, you were used to using the @export property. In the shading language, we use a different keyword called uniform. And then we always specify the type first. So, in GDScript, we would have typed a texture 2D here. Here we have a type sampler 2D. And let's call this team palette. Okay, and as soon as I press the save button here, you'll see that on the right-hand side, there is a new section called shader parameters. And we can set these initially, which will remain, or we can also set these in the code. So for now, let's go ahead and find our palette. So type palette inside your folder here, and then drag and drop the team's color palette all the way into the team's palette property. Okay, and the second parameter that we want to pass into our shader is which country we want, or pretty much like which row we want to do the lookup from. Earlier we were talking about Germany being the 6th row, or the row index 5 when it's 0 indexed. So let's go ahead and have an integer that we can pass in to specify the index of the row. So once again, uniform instead of export, and then here we'll need to specify the type, which will be an integer, and then let's just call this team color. And by default it's going to be 0, but let's go ahead and set this for Germany. So we said it was index 5. Okay, so now that we have those things properly set up, we need to think about how to write the code inside our Fragment function. Now, the code that we're going to be writing here is going to be very similar for swapping the colors of the skin. We're going to just have a different palette, but it's going to be roughly the same. So rather than have to write the code twice inside the Fragment function, what we're going to be doing is writing a separate function that will be called from Fragment for both of our cases. So let's go ahead and create that function. And basically, we want to return another color. So it's going to be vector4. So in the shading language, you always specify the return type first, and not after with an arrow like in GDScript. And then let's call this get palette color. And it will take 3 arguments. The first one being the original color. The second one being the image, the palette that we need to pick from. And then the third one being the row. So let's call this selection. And by default, we're just going to return the color that is being passed. Okay, so we can now call this method and change the color. Color equals get palette color. We're going to pass the current color of the pixel. Let's pass the palette up for the team, and let's pass the color. Okay, so right now this, basically doesn't do anything because it just returns that same color that gets passed here. But down the line here, we're going to be doing our lookup. So, okay, so what do we need to do our lookup? Well, we need to look at the various pixels of this image one by one, starting with the first row of reference, and to find which column to be on. So ideally, we have a function that allows us to pick the color of the pixel at a specific location of this texture. And luckily, the OpenGL Shading API does provide a function to do this right out of the bat, a function called texture. And texture takes 2 arguments, the first one being the sampler to image. So here we can just pass in the palette. And the second one being the location. Where do you want to do that lookup? So here, if we wanted to do a lookup at position 4 and 3, for example, the 4th pixel to the right and 3rd pixel down, you might think that we could just write 4 and 3 here. Unfortunately for us, this does not work. If you look at the documentation for the texture method, you will see that the second argument doesn't take a pixel location. It takes something that's called a UV coordinate. So what the heck is a UV coordinate? And you'll see that concept across the board all over the place whenever working with shaders. So it's really important to understand what UV parameters and UV coordinates are. So let me just take a quick minute to explain what it is. All right, so we're going to be using our palette texture here to illustrate this new coordinate system, but let's just assume that this texture is generic and has a size of W pixels for width and H pixels for height. So in this case here, we have 6 pixels for the width and 9 pixels for the height. So you're already familiar with the pixel coordinate system. And for example here, if I wanted to look up the pixel at position 3 and 2, and given the fact that this system is 0 indexed, then I can just navigate to the 4th pixel from the left, 0, 1, 2, 3, and then the 3rd pixel from the top, 0, 1, 2, to get that specific pixel at position 3 and 2. And when working with textures in shaders, we actually use a different coordinate system that is called the UV coordinate system, also called the texture coordinates. So the way that UV works is quite simple. Basically, it maps a coordinate system to a texture. The coordinate system only exists within the dimensions of the texture, so the horizontal axis actually takes the full width of the texture and is called U. And similarly, the vertical axis takes the full height of the texture and is called V. And both of those axes go from 0 to 1. So because U and V actually take the full width and height of the texture, they're actually completely dependent on the size of the texture. So if you were to pick a different texture with a different size, you would have different U and V vectors, which would have different sizes altogether. So again, U and V are completely tied to the texture, the size of a texture. So knowing those axes go from 0 to 1, and our image is currently W pixels width and H pixels height, can we try to place some units on those axes? Well, on the U axis, if U goes between 0 and 1, and we know that the width of that texture is W, then after a full pixel, after we reach this distance here, we'll actually have reached 1 divided by W. And we can go on until the end of the second pixel, where we will reach 2 over W. And we can go on and on all the way until the end of this axis, where we will have reached W over W, which again equals 1. So if we do the same thing on the V-axis, we now have units that we have currently placed on our texture in this new UV coordinate. Now, the problem that we want to track here is we want to be able to pinpoint a specific pixel. So I'm just going to pick back on the same pixel that we had earlier, which is currently located at position 3 and 2 in our pixel coordinate system. So what do you think is the best horizontal value and vertical value for U and V to represent this pixel inside this new coordinate system? Well, what happens if we pick 4 over W and 3 divided by H? Well, you can see here that the resulting coordinate is actually at the intersection of 4 different pixels: this blue pixel, this gray pixel, yellow and orange pixels. And this isn't exactly quite what we want. We actually want to be able to pinpoint that blue pixel here. So we want to pick values for U and V that actually, where the intersection is actually inside this blue pixel. And if you want it to be as precise as possible and aim for bullseye, well, you probably aim for the very center of that pixel. So in our UV coordinate, that blue pixel at position 4, 3 would be represented, well, would be best represented by the UV coordinate 3.5 over W and 2.5 over H. And here, as you can see, we're talking about fragments or divisions of pixels, and that's perfectly fine when we're talking about textures. Again, there are other values that would map to this blue pixel, right? Like basically there's a range for U and V where we would land inside this pixel. But for now, we're just going to aim for the center, and we can write a very quick simple function that translates our pixel coordinate into our UV coordinates. And that way we just won't need to worry about thinking too much about UV. So the function is quite simple. We basically take our pixel coordinate, add half to it, and then divide that by the width, and then do the same thing for the height. So let's go ahead and insert that into our code, and we can use that to get the pixel color of a specific texture. All right, so let's go ahead and write our function to transform our pixel coordinates into UV coordinates. First of all, I'm just going to increase the size here just to make sure you can see properly. This screen is a little bit small. And then also, just to make sure we see this properly, I'm going to hide the various collision shapes that we have. Okay, so let's start by creating that function. So we are going to return a vector2 of pixel to UV, and here we're going to pass the pixel coordinates and the texture size. Okay, and we want to return a vector2 for the U value. We want to find the x position of our pixel coordinates. We want to add half of it, so we aim for the center. We want to divide this by the width. And then we want to do the same thing for the V coordinates. So we pass in the Y pixel coordinate, add half, so that we aim for the middle, and we divide this by the height. Okay, so this works well, except the only thing here is in GDScript, when you work with vector2s, GDScript doesn't really care whether you have floats or integers or different types inside your vector2s. In the shading language, it cares actually quite a bit about this. And so our pixel coordinates are going to be using integers. Same thing for our texture size. We were talking about the number of pixels in width and height. So actually the proper type here when using vectors is using an I vector, which means that those vectors are full of integers. And this is going to complain a little bit. We do want to return a floating point vector because these are UV coordinates. We just need to cast some of those values to float. So let me just add a couple of functions to transform our integers into floats. And in order to use our pixel to UV method, we actually need the size of the texture, which we currently don't have here. But luckily, once again, the shading language provides an API right out of the box for this, which is called texture size. And it currently returns an IVEC2. And this takes two arguments, the texture itself, which on our end is the palette, and a second argument called the level of detail. This is also called the map level. 0 is the default and basically represents the texture at full resolution. But then every time you increase this by 1, it basically shrinks the texture in half. And it just keeps going and going until it reaches a size of 1 by 1 pixel. This is useful when the texture is far away from the camera. You don't necessarily need to render it at full resolution. So you would increase that number here. And it's just a way for you to optimize your rendering. So on our end, we do want the texture to be here at full resolution. So we're just going to be using 0 here. All right, so what do we want to do? We want to loop over that first row here, the reference row. So let's go ahead and create a for loop. We'll go all the way until the full width of that first row. Okay, and first let's get the pixel, let's get the UV coordinate for that pixel. All right, so we'll pass in the pixel coordinate, which is going to be at the first row and then the eth column, so the eth element, and then we'll want to pass in our texture size. And we want to get the color for this. So again, the color returns a vector 4. And here we'll want to pass in, this function here. Except instead of using this vector 2, we're going to be using this new UV coordinate. Okay, so now that we have the color of that pixel, as we go over that first row, we're going to compare it with that color of that we're being passed from the fragment shader. If we do have a match, then that's great. We already know which column or which row here we want to pick the pixel from. So we can actually, once again, let's do a lookup into that pixel. We're going to need the UV coordinate. All right, so this is the ith row, and then this selection here provides us where to go in our texture. Okay, and let's find the actual color from that pixel. And if I'm not mistaken, as soon as I enter this line, we should actually have a little bit of a magical moment here, so I don't want to ruin it. There we go. And as I saved, we can see now that the colors of the jerseys have been replaced with the colors from that row here for Germany. And as I tweak the parameter here and I go up, you can see now that we actually have all of the colors for the various jerseys. And just like that, we now have a fully customizable player that can be recognized just by setting a simple shader parameter. So I'm going to pause here for just a little bit. I'm going to increase the size here just to make sure that you're all fully aligned on what's happening. So we start off in the fragment shader. This is going to be executed for every single pixel, including the transparent pixels, including the hair, including the skin. All of the pixels are going through this. We're calling the method getPaletteColor. Here we're passing the color of the pixel that we currently are on, the palette, and then the country or which row we want to aim for. And then the first thing that we do is we get the coordinate for those that reference row, so we can get the color of those pixels. And there's only 6 of them, so we're comparing the current color of the pixel with one of those 6 colors. And if we do find it, then this means that the color is that pixel is currently one of the equipment, one of the jersey. Part of the jerseys. So we want to find out by which color we need to replace it, and we do another lookup here in order to find the correct pixel, and we get the color which gets replaced back inside the fragment shader. So hopefully this makes sense. And just to make sure that everything is clear for you, I'm actually going to have you do a little bit of an exercise. So while we replace the colors of the jerseys, we still need to replace the colors of the skins. And here you have another palette which works exactly the same way, with the first row being the reference and then other colors down the line. I want you to try and see if you can adapt this shader and reuse this method here so that you can actually change the colors of the skin. So go ahead and pause the video now, see if you can do it, and then come back to see if you have the same solution as me. All right, well, hopefully you were able to try out this coding challenge, but if not, that's perfectly okay. Just follow along with me. So here we're going to need a couple of additional parameters that needs to be passed to our shaders. We'll start off with our skin palette. Again, this will be a sampler 2. And I'm going to be dragging this skin colors palette image over to my skin palette shader property. The main difference here between the two palettes is that in the team palette, I had a row of reference colors at the top. Here, I don't have that. I just have the light color, medium color, and dark color. So this means that if the player currently uses a light skin, we probably won't need to do any replacement whatsoever. Okay, so the next thing we'll want to do is add which row we want to target, whether we're targeting the medium or dark. So let's do uniform and skin color. And a couple of things that you can do to make the parameter section a little bit better. First of all, we can group some of these, and you can do this using the keyword group uniforms and then the label of that group. So here, for example, I'm gonna do that for the palettes, and just don't forget the semicolons at the end. And so when I save here, you can see now that we have a section, dedicated section for our palette parameters, and you can just set those properly. It doesn't change anything, it just makes it a little bit nicer to play around in the editor. And then second thing that's also nice to use is we can actually have drop downs rather than have like integers here. We can have drop downs with enums that represent what we want. So for example, here for the skin color, I'm going to use this, and we do this using a keyword called hint enum. Okay, and when I save here, you can see that the values 0, 1, and 2 have been replaced by these enums. And the nice thing about this is that it kind of limits the range, right? Like this team color here, you can go as far as you want, whereas the skin color now is limited to the values 0, 1, and 2. So anyways, you could do that for the team colors if you want. Okay, so what is the script going to look like? Well, it's actually pretty straightforward. So here for every pixel, we try to change the color by looking at whether we have a color of the jersey, like any pixel that belongs to the jersey would be changed here. But you know, if we have a transparent pixel or a skin pixel, those pixels don't get affected by this function call here. So first, we can check if our skin color is greater than 0, and that's the only case we need to make any changes, because by default, we're using the light skin color. If that's the case, then let's try to change our color as pixel to the skin palette. And we'll use the skin color. Get palette color. There we go. And just like that, if we now change the color of the skin to medium and dark, we should now have the proper response in our shader. Okay, so hopefully you're able to do this, and you can see just the power of using shaders, how quickly we can, you know, create new type of players by just changing these settings. And you know, typically in the code down the line, we will be doing this dynamically. This will allow us to have you know, two teams with the various properties and rosters that look more diverse than they are today. But in all of your games, you can use this to change you know, things on the fly, right? Like for example, say you wanted to get your character to become dirty over time, you can just you know, change the colors and make them darker. Like all of those things are available through the power of shaders. And hopefully you're able to understand how this works. It's a pretty straightforward one. There's a lot of more complex things that we could be doing down the line, and it's just super interesting. So let's go ahead and implement this in our code so that when we start the game, we actually have the proper jerseys and skin colors. Okay, and just to make sure that everything works properly, I'm going to set the team color back to the default colors. And that way, if they end up being the default color when we run the game, we'll know that something wrong has happened. Okay, so we want to make some changes to the player script. So hop over into the player script. And here you'll notice that we currently don't have any notion of country as part of the player script. So we could either store the name of the country or the index of the row where we have the country where we can pick the shader from. Let's go ahead and add a constant instead and just have the list of countries. So COU. And I'll call this country map, and I'll just, actually, let's just make this an array. So countries. And I'll just list in order, the countries in order by which they appear inside the texture map. So we added Canada earlier, and we would need to add a new row with that palette. So feel free to do this, but I do want to check the fact that sometimes you may have a typo or use a country that currently doesn't exist, and we just want to make sure that everything still works properly, in which case it should be using the default skin. Germany, Italy, Spain, and USA. All right, so where do we set this country? Well, whenever we initialize the player, it's probably a good place. So here we're going to need another property. And then let's just set it here. We need to add a variable for this country here, which we don't have. By default, I'm going to make this an empty string. Again, I want to make sure that everything works properly. So if we don't modify this, by default, it's going to use an empty string, which is going to use the default country here. And this will refer to that first row at the top. Okay, so then we want to actually set the shader properties. And so this is going to be affecting the player sprite, which is going to be a child node. So we want to make sure that we do this as part of the ready function, where all of the children nodes are available. So let's create another function for this. And maybe just right here, we can create it. All right, so how do we set shader properties? Well, if you hover over the name of the property here, you'll see, so it's a little bit cut off on my end, but you'll actually see the name of the property that you can affect and modify inside our code. So to do this, we basically call our player sprite, and we want to affect the material. And then there's a method called setShaderParameter. Okay, and we're going to be doing the same thing for the countries, except first of all, we need to figure out what is the index of the country. And so let's pick the color here. And let's actually call the find method. So that way, this may actually return -1 if we have an issue with the country that we've sent. Let's say in our JSON file, we have a typo, or something that goes wrong, we have a country that isn't listed there, then this will return -1. So then let's go ahead and clamp the value. Between 0 and the size of our array. And that way we'll make sure that the color is a color that exists. So it's always going to be between 0 and 9 or 8, whatever the value we have there. Okay, and then now we want to set the parameter in the shader. So let's go ahead and copy and paste the same line here. And then here we'll want to change the team color to this country color. All right, now going back in time, we need to we've changed the signature of the initialize method. So back in the actors container here, let's make sure that we initialize with the country, which we need to pass in the signature of the spawn player. And again, which needs to be passed here when we invoke that method. Okay, so let me go over the script real quick. So whenever we spawn players, we pass in the country information, which gets passed inside the initialization of the player. Here, we're basically just setting we're already setting the skin color. We're now setting the name of the country. And then as part of the ready function, we're using now a new function called setShaderProperties, which basically set the value for the shader parameters that we've set up earlier. Okay, and this might not work. Okay, let's try it out. I think there's one more thing we need to do here. Okay, so here, this is great. We are seeing some changes. We're not seeing the default skin. However, we're seeing that everyone is dressed as the Germany and everyone has a dark skin. And you might be wondering why that is. Well, the reason is that by default, all of the materials are shared amongst all of the resources. So if you hover back over on the player sprite here, this material is going to be shared for all of our players. And this is good. It's a way to optimize the Godot game, but we actually don't want that. We want every player to have their own material. So in order to do this, you can actually click here on resource and you want to set local to scene, which means that every material is going to be local to the instances of the scenes that we have. And now if we press F5 once again, we should have our players properly done. Except here, and this is great because we double check that Canada, which is currently not supported in our palette, still works, right? You can still play around with it. This is going to be the default jersey for Canada or for any teams that we don't support. But here you can see that Germany is set up properly. You have all the right skin colors, you have the right jersey colors. So feel free to add some colors for Canada as the last row here in our palette. On my end, I'm just going to change the name of the team. Sorry, Canadians. I do want to keep the resource the same way so that when people use the project, they have the same file here. So here in my actors container, I'm just going to replace Canada with, let's do Spain, and run the game and just make sure that everything's working properly. And there we go. And this player I can see is actually running quite faster, so I must have picked a good player. But you can see here that we now have fully working jerseys and skin colors. That adds a lot of diversity to the game, and it makes it a lot easier to know, how to play the game. And this is a perfect place to save our changes. I'll add all of them, and I'll commit them under the message added shader to replace colors. And I'll push my changes on the internet. Okay, and with this Fragment shader implemented and now working in our game, we almost are at the 1 hour mark. So this is going to be it for this episode. I know we went well over the allocated time today, but I expect this to probably be one of the longest episodes of this series. I really felt important that we shouldn't skim over any of the details, so I did want to make sure to cover as much as possible. It can quickly become confusing to understand what's going on when we work with shaders, so make sure that you fully grasp everything that we talked about today. And hopefully, as you can see, writing a shader isn't that different from writing just regular GDScript code. But because it's executed on the GPU side and it's executed in parallel for all of our vertices or all of our pixels, it does use a specific language and API, and it does come with its own set of specific considerations that we need to take into account. But other than that, shaders aren't that complicated. There's no magic there. And, the shading language uses some familiar C-type syntax, which is quite similar to GDScript and Python. So hopefully it shouldn't be too complicated for you to start embracing that and writing your own shaders. And Godot actually makes it quite easy to write shader code. It does a lot of the boilerplate initialization for us, and this just opens up a ton of possibilities with using shaders in Godot. So we've only scratched the surface today, but hopefully it make complete sense to you. And if it didn't, well, once again, you know where to find me, so just poke around in the comment section below. So I hope this was a useful episode for you, and if you hadn't heard of shaders before, or if you were somewhat hesitant to drill into writing shader code, I really hope that this episode opened up the door for you to feel more comfortable creating your own shaders for your own games. You'll be surprised to learn that there's actually entire jobs out there for just writing shader code. And as usual, the more you do of it, the more comfortable you'll become, so the easier it will be for you to write shader code. So with that said, if you did like the content today, please go ahead and support the channel using the like and subscribe buttons. And once I reach my goal of hitting 1,000 YouTube subscribers, I'll go ahead and have you guys pick the nature of the next tutorial series. In the meantime, time to take a quick break, and I'll see you in the next episode. Cheers.